So in question number 9, we have a uniform electric field that's directed out of the page in a circular region of radius 3 centimeters. You'll see it overdrawn over to the side. The field magnitude is given by this expression, 4.5 times 10 to the minus third times t, where t is in seconds. What's the magnitude of the induced magnetic field at a radial distance of 2 centimeters and 5 centimeters? So first of all, figuring out at 2 centimeters, that's within the circle, and that's sort of given by this point right here. And we're trying to figure out the magnetic field at this point or any point along this circle. If we solve it, we're going to be using Maxwell's modified equation. In this case, there's no conventional current, so this term is simply 0. And what we have here then is mu naught epsilon naught, the change in electric flux being electric field times area, over dt. In this case, it's going to be the circumference of our circle is going to be the integral of ds because the magnetic field's constant along here. And I'm going to move out the area out of the flux. So again, remember, this is equal to electric field times area. In this case, the area is not changing. It's only the electric field. And we can actually solve this. Now, the area here that we're talking about is just the area within this shaded region over here. So in this case, the r's in this case are both the same. It's going to be 2 centimeters here and 2 centimeters here. So I can actually do a little bit of reduction here, divide both sides by pi and r. Or I guess in this case I didn't. And you're going to be taking the derivative of the expression for the electric field. Remember, that was given up here. Luckily, this is pretty simple. The derivative of that with respect to t is simply that number. And so we end up with that. And when you divide this out, yeah, we lose a pi here, we lose a pi here. We can cancel out one of these terms right here, giving us just that. And you can take it just a little bit further if you want and go ahead and solve it there. And yeah, you could plug in mu naught and epsilon naught and get a clearer expression, but I just left it there. All right, second part of this one. The question is now, what is it out here? Now, you're like, oh, okay, same. Yeah, in a lot of ways it is. This term's still 0. There's no conventional current, only a displacement current. That's supposed to be an arrow. And then down here, the only tricky part on this one is the area here. This is the area where the flux is occurring, and that is only going to be in this region right here, which has a radius of 3 centimeters. It's not the entire thing. Whereas the radius here is the radius of our entire Amperian loop, where we're trying to find the magnetic field, which is going to be pointing this way, just out of curiosity, just if you're curious. And that's the same everywhere along that. So when we solve this time, again, we're going to place the area to that. And in this case, the radius here of our loop is 5 centimeters, but the radius where the flux is occurring is only the 3 centimeters. And again, we're taking the derivative of the electric field with respect to time. That's pretty straightforward. And if we solve this, we end up with this expression right here, and if you multiply that out, you get that. Again, you could actually go ahead and plug in mu naught and epsilon naught and get the exact number. I just left in terms of that. Hopefully it makes sense. The tricky part on this one is realizing what area the flux is occurring. In this case, when you're outside of it, it's only the region where there is a change in flux, not the entire thing. Whereas here, when our loop was inside of it, our area was that portion. Good luck. Hopefully that made sense. Talk to you soon.